All right, let's dive right into this explainer. Today, we're breaking down the absolute foundational building block of artificial intelligence, the perceptron. If you've ever looked at modern deep learning and wondered, how on earth does a machine actually think or make a decision, well, you are in the perfect place. We're going to strip away all that dense jargon and step onto the absolute ground floor of neural networks.
So how does a machine actually learn to make a decision from absolute scratch? I mean, that really is the million-dollar question, right? Rather than starting with complex calculus or talking about massive data centers, we're going to answer this by going on a little mission. We're going to figure out a completely unknown rule from scratch, and we're going to do it exactly the way a basic AI model does.
To pull this off, I want you to imagine we're standing right on the lunar surface. Our mission? We need to figure out exactly how fast we need to go to escape the moon's gravity. But here's the catch. We don't have a physics textbook. All we've got is a rocket and the ability to run trial flights. So we're going to learn the escape velocity of the moon strictly by trial and error.
Okay, let's look at the data we've gathered from our test flight so far. We're acting like detectives here, gathering clues. First, we launch at 1.0 kilometers per second. The result? Nope, we crash right back down. Then we crank it way up to 5.0 kilometers per second. Success! We leave the moon. We try 3.0? Yes, success again. We drop back down to 2.0? Ah, no, stuck on the surface. We try 2.5, and yes, we escape. Finally, we test 2.2 kilometers per second, and nope, we fall back down. Just by tracking these trial results, you can see our suspect pool is rapidly narrowing down.
So the really crucial point here is that intuitively, you and I can already see the pattern. Just by looking at those numbers, we know the actual turning point, the exact escape velocity, has to lie somewhere in that tiny gap, strictly between 2.2 and 2.5 kilometers per second. Now, you and I did that in seconds, but the whole goal of machine learning is to teach a computer to draw that exact same line on its own, based purely on the data.
To automate this whole process, we need to build what's called a classifier. Simply put, a classifier is just a function that takes our input, which in this case is our trial speed, and spits out a simple binary decision. Do we leave the moon, yes or no? Basically, it's just a mathematical sorting machine.
And that brings us to the real star of our explainer today, the perceptron. Originally developed decades ago, the perceptron is the most basic, fundamental version of this classifier. What's super fascinating about it is that it was actually inspired by biology. It was designed to mimic human nerves firing. Think about how a neuron in your eye acts like a light sensor, right? It only fires a signal to your brain when it detects a certain amount of light.
And this brilliantly illustrates how a perceptron really isn't some scary, magical algorithm. Honestly, it acts just like a simple binary switch. Think of an automatic light sensor turning on your porch bulb at dusk, or, your household thermostat. A thermostat doesn't do complex calculus. It just simply activates the heater when the room temperature drops below a specific physical threshold. The perceptron does the exact same thing, but it activates or fires a yes decision when the mathematical input crosses a specific numerical threshold.
So let's see how this actually translates into a step-by-step classification trial for our machine. First off, we feed the model our tested velocity. Second, the model compares that velocity to its current internal threshold, which we'll just call t. And finally, it outputs its decision. If the input is higher than the threshold, boom, it says yes. If not, it says no. Mathematically speaking, we call this a step function. You can really see the logic here. If our input velocity, let's call it x, is greater than our rigid threshold t, the model fires and outputs a 1. It essentially shouts, escape. But if x is less than or equal to t, the output is a big fat 0, stuck. This simple logic is the core engine of the perceptron's entire decision-making process.
Now, what's really interesting here is this incredibly elegant math trick that AI researchers use to make this system actually capable of learning. You see, having a rigid threshold sitting on one side of the equation is kind of clunky for a computer to update. So we change it up. We start with x is greater than t. We smoothly move that t over to the other side, which gives us x minus t is greater than 0. Then we just substitute that negative t with a brand new variable called a bias, or b. So our new, much cleaner equation is simply x plus b is greater than 0.
So what exactly is this bias? Well, by switching from a fixed threshold to a bias, we're essentially giving the model a built-in slider. It's an adjustable parameter that shifts the activation point left or right. Instead of the model trying to constantly redefine the rules of the threshold itself, it just bumps this bias slider up or down. It makes its whole optimization process much, much easier.
With this slider in place, our entire mission completely changes. We're no longer randomly guessing speeds. Our goal transforms into a simple optimization problem. The machine just needs to find the exact bias value, this one-dimensional vector, that perfectly separates our yes trials from our no trials. We want that equation, x plus b is greater than 0, to be true only when we actually escape the moon.
So, how does the machine find that perfect slider position? It enters a learning loop. First, it guesses a random bias value. Second, it checks what we call a cost function, which is honestly just a fancy way of asking how many errors did this guess make against our test data. Third, it uses gradient-based optimization to nudge the bias parameter in the direction that reduces those errors. The model learns by automatically repeating this cycle over thousands of iterations. Guess, check, update. It's slightly tweaking the slider every single time until the errors are practically minimized.
And look at what happens when we actually run this with our Lunar data. After iterating through the trial data, the model's cost function drops, the system stabilizes, and it learns this highly specific bias value, -2.503. Remember how earlier we intuitively guessed the threshold was strictly between 2.2 and 2.5? Well, the model found it entirely on its own. By arriving at this exact number, it successfully taught itself the escape threshold from absolute scratch. Which brings us to the absolute most exciting part of this entire concept. What we just walked through was a single perceptron. Literally one input, one bias, one simple switch deciding yes or no. I want to leave you with this provocative question to ponder. If one simple mathematical switch can learn this threshold entirely on its own, what could millions of these switches, all connected together in vast, overlapping layers, achieve? Well, that is exactly what modern deep learning is. Thank you so much for joining me for this explainer, and keep questioning how the digital world around you actually learns.